So now we're going to consider first order series RC circuit. Then in the next lecture, we'll consider first order parallel RC circuit. So we'll do the same for RS circuit as well. So if we have a voltage source connected in series, the resistor, and then also in series, the capacitor, you observe that the series connection between the voltage source and the resistor forms a Thevenin equivalent circuit. Okay, so let's say this is VT, this is RT. So that this is a capacitor C, plus or minus VFT. Okay, and then the current that flows through this is I of T. And this is plus or minus VR T. So say this combination is the Thevenin circuit. Okay. So meaning, should we have a number of resistors in the circuit, we could resolve to come up with an equivalent resistance connected with the voltage source as the Thevenin equivalent circuit, and then connect in series with the capacitor, which still forms the RLC circuit. And to resolve this is pretty straightforward. We first have to develop the mathematical model that describes this circuit. And once we do that, we can now, we may now figure out the best mathematical approach to address the resulting model. Okay. So the first thing to do here, since we have series connection, we can apply Kirchhoff's voltage law. So by Kirchhoff's voltage law, we have the negative V sub T of T plus V R T plus V of T is the same as 0, where VT T is the same as VR of T plus V of T. Okay? And by law, we have that VR of T is the same as the current through this resistor times the resistor of the R T T. And now, by the element constraint for the capacitor, we have that I of T is the same as C dV of T dt. Right? So that this expression that describes this RC circuit may now be written such that we are able to substitute the values, right? So we can plug in VR of T into this. And once we do that, then we can also plug in the value of I of T into this, so that this equation will now become So plug this into it, that is Vt of t will be VR is R t. Now I of t is C dv of t dt plus v of t is equal to 0. So it's, yeah. So the quality is already there, except we post the quality sign again. Okay. Now, you'll observe that this is a first order differential equation where the unknown function is the capacitor voltage. Okay. V of Ct. Now we know the source voltage, we know the resistance value, we know the capacitance value, but now we have to figure out the capacitor voltage, okay? So first of all, it's a first order differential equation, D, okay? Because this is the order of this differential equation is 1, not the n of, and then the unknown is a capacitor voltage. V of t. And this capacitor voltage, V of t, is usually referred to as the state variable. Because the capacitor voltage describes the state or the behavior of the circuit at any time. Okay, so the thing that determines the state or the behavior of the circuit is the capacitor voltage. Okay, so now that we have the first order differential equation, recall that the solution the differential equation mentioned earlier is the sum of the zero input, zero input response is the zero state. This is what we now have to address based on this equation. Okay, so now that we have to address two major things, zero input response and zero state response, we may now reorganize the circuit based on what we described in the previous lecture. Now, we already have circuit is a voltage source. So we have Vt of t. So let's say this is a unit response, a unit step. We have Rt being Thevenin equivalent resistance. We have a capacitor, plus or minus. Now here, we're able to tell the initial value. Initial value here is V0, right? So for zero input response, we mentioned in the last lecture that the input or the forcing function is reduced to zero, is the same as zero. So it means for us to be able to address the zero input response, we can redraw the circuit to look something like this, where the forcing function is the same as zero. So that's Vt is equal to zero, right? And then what we now have to do, we now address this RT, address or resolve the circuit based on the initial condition. So this is when we consider zero input response. When we now have to consider the zero state response, we have the forcing function, plus minus, we have the forcing function, and then the initial condition will be reduced to 0. Then we have equivalent resistance and our voltage source. So this is for zero state response. So these are the two circuits we will now have to resolve. And we know that our total solution is the same as zero input response plus zero state response, where our zero state response is the same, is the sum of the homogeneous solution and the particular solution. So let us begin with the zero input response. So you want to recall that, so, okay, evaluation of the zero input response, right? So you want to recall our differential equation based on the circuit is the same as RC dV t dt plus V of t, where V of t is the state variable, okay? And now, since we want to resolve the zero input response, then we can actually replace V of t with VZI of t, okay? So that where V sub t of t is equal to 0. So it means that we now have RC dVCI of t dt plus VZI of t is equal to 0. So you want to recall for an LTI system that we said our test or guess signal is the eigenfunction, which is the EST, okay? And in our case, we could use it as EKT or EST or whichever, okay? Now, if VZI of t is the same as EKT, for instance, excuse me, then if we feed this into a system, having this as a test signal, then it means that VZI of t could be assumed to be, say, AEKT. Okay? In this case, the A and K are some arbitrary constant of the zero input response. Now, when we adopt a different approach to solving this problem, in the case of the parallel combination, we will derive this, okay? So we know it's not just an assumption, but we already know that once we feed the eigenfunction, say EKT, into an LTI system characterized by some parameter H of K, for instance, now the output is going to be H of K EKT. So it means we are getting a replica of the input at the output, but scaled by the parameters of the system. Okay, so that is similar here. So it's an assumption we are making, which is consistent to reason and provable. Well, we're going to resolve that in the next video. Now that we have this assumption in place, we can as well substitute for VZI of t with A EKT. So that R C D the A EKT dt plus A EKT is equal to 0. Okay. Now, once we differentiate this, we are going to get the same thing, right? So that this will now be R C. So it should be A K. The A EKT will be K A. That's EKT. The K E K T. KT times A plus A EKT is equal to 0. Okay. So from this, we have A EKT is equal to negative, this crosses the equality sign, or C K A. Okay. And then this also is the same as AEKT plus RCKAEKT equal to 0. So that we now have AEKT is common, 1 plus RCK equal to 0. So that 1 plus RCK is equal to 0 over AEKT. 1 plus RCK is equal to 0. Okay? You now observe that the characteristic equation of this differential equation being 1 plus RCK will now be such that K will be equal to, if this crosses, so let's say RCK equal to minus 1, so that K will be equal to minus 1 over RC. Now that we have been able to resolve the value of K, we can now plug that into the solution, which we assume or guess, right? So that VCI of T will now be equal to A epsilon minus K is now 1 over R C T. So minus T divided by RC. Now, the next point to look up is A. What is A? Now that we have been able to evaluate BCI of T equal to A epsilon minus T over RC, to evaluate A, we need to apply the initial conditions, okay? That is, at T equals 0, VCI of naught is equal to V naught, right? So that here, at VCI, T equal to 0, initial condition, then A epsilon minus 0 over RC will be A epsilon 0, which is epsilon 0 is 1, A to the power 1. Okay? And this we know is the same as VCI of naught is equal to V naught, so that A is equal to V naught. so that now the zero input response will now be VCI of t will be V naught epsilon minus T over RC. Okay, which can also be written as V of naught epsilon minus T over C. Okay, where V naught is the same as V of naught. Okay. Now you observe that RC is the time constant, usually addressed as tau equal to RC. Okay, and it is a measure of how long a capacitor has either charged or discharged. And this usually takes up to 5 time constants. Okay. Now that we have been able to address the zero input response of the circuit, the next thing is to evaluate the zero state response. Okay. Now you recall that for the zero state response, we said, well, we have the source, and then we have the capacitor. This time, the initial condition is 0, and everything depends on the input source, which is the same as U of t, and then t, okay, for a zero state response. Okay, now to evaluate this zero state response, we said zero state response is the same as the homogeneous solution plus the particular solution. And for us to compute the homogeneous solution, we evaluate the zero initial condition, right? And recall that V, the input signal, is the same as a step function. And for a step function, it is 0 at t less than 0, and it is 1 t greater than 0. So we have something like this. Okay, this is a step. So at this point, this is t greater than 0, this is 0, and at this point, this is t less than 0. Okay, so it is 0 at t less than 0 from this point this way, and then at some time t greater than 0, it is equal to 1, right? So it means that the input function is divided into two parts. So it means U of t is equal to 0 for t less than 0, and U of t is equal to 1 for t greater than 0. Okay? So we will now evaluate the homogeneous solution at U of t equal to 0, and then the particular solution at U of t equal to 1. So at t less than 0, U of t is equal to 0, and here we can resolve the homogeneous solution. And in this case, we address this as VH of t. So say this is homogeneous. And we already know that U of t is equal to 0. We call our mathematical model, for which we have RC, the VH of t dt plus VH t. So we are resolving at t less than 0. so that this is 0, so that V H of t will be equal to negative RC dVH of t dt. And this is similar to what we already solved for the zero input function, zero input response rather, so that VH of t, so that VH of t will now be the same as C1 epsilon minus t over C. So we don't have to repeat the entire process. Now, you observe that this constant C1 cannot be evaluated till we must have solved for the particular solution. So C1 will only be determined after the evaluation of the particular solution, and then after applying the initial condition at V0 equal to 0 volts. So the next point is to solve for U of t, when U of t is equal to 1, t greater than 0, so we now have the particular solution. Okay, then we can replace this with Vp of t. Okay, so after t equal to 0, we see that U of t is equal to 1, right? So it moves from 0 to 1, which is equal to RC. We call as model, the mathematical model for the circuit. So that will be the Vp of t dt plus Vp of t. So this is at t greater than 0. So recall, this is the solution we have for the homogeneous solution, and we can only solve for C1 after we must have solved for the particular solution. And now we have to address this problem. Okay. And in this case, we have a step function. So let's write this. And then U of t equal, which is equal to RC dV P of t for the particular solution dt plus Vp t. Okay. Now, for the step function, the output is constant after t equal to 0, because this one. So after t, this is t less than 0, this is t greater than 0, and this is t equal to 0. So after t equal to 0, this output value is constant, it's 1, all true. So the particular solution always depends on the actual input signal, like I mentioned. So now that we have a step function, it means the particular solution is going to be a constant. If we had a sine or cosine input signal, then the output would be a combination of the input and output. So since the particular solution is a function of the type of input, and since we have constant input, so it means that the solution Vp of t is constant. Okay, so we can assume this constant to be some value Va. Okay, if we make this assumption, for instance, we see that after t equal to 0, we already have the system is energized. Okay, so since the system is energized after t equal to 0, this describes the transient voltage behavior. Okay, so after t equal to 0, the unit step U of t describes transient voltage then the capacitor voltage responding to the step is called the step response. Okay, and then the capacitor voltage responding to the step response, is called, or to the input rather, let's put it that way, responding to the step input is called the step response. Okay, so now that we have done this, we now see that when we replace this Vp of t with Va, so it means that U of t, which is 1, will now be equal to Rc, the Va, which is a constant dt, plus Va. And once we differentiate a constant, it is 0, right? So this is going to give us 1 plus Rc into bracket 0 plus Va. So equal to 0 plus Va. So it means Va is equal to 1, which is consistent with assumption because the step function is 1, and since the particular solution is depending on the type of input, and we already said if it's a step function which is a constant, then the particular solution must be a constant, so that justifies our point. So the 0 state response will now be the homogeneous solution plus the particular solution, which will now be VZS of t will be equal to C1 exponential minus t over RC plus VA. So now that we have that, so we may evaluate C1 by applying the initial conditions. T equal to 0, and VZS of 0 equal to 0 volts. Okay. So once we do that, it means VZS of t is equal to C1 exponential minus t over RC plus VA. T equal to 0. VZS of 0 is equal to 0. So that VZS of 0 will now be C1 exponential minus 0 over RC plus VA. So this will be equal to 0. VZS of 0 is 0. C1 exponential 0 will give us 1 plus VA. So it means 0 equal to C1 plus VA. So C1 is equal to minus VA. So that VZS of t will be equal to negative, so we're going to plug that into this, negative VA exponential minus t over RC plus VA. So this is same as VA minus VA exponential minus t over RC. So that the 0 state response is the same as VA into bracket 1 minus exponential minus t over RC. Now that we have done this, the total solution will now be the same, that is V of t now be the same as the zero input response, V of Zi, V sub Zi of t plus the zero state response solution, V sub Zs of t. This is going to give us V naught exponential minus t over RC plus VA into bracket 1 minus exponential minus t over C. So we can also open this up to say V naught exponential minus t over RC plus VA plus VA exponential minus t. This is going to give us VA plus V naught exponential minus t, collect like 10 minus VA exponential minus t over C. Then this V of t will be equal to VA plus V naught minus VA exponential minus t over C. Okay. This also could be written as V of t is the same as the final solution, infinity, plus the difference between the initial solution, the final solution, exponential minus t over C. We can also write this as the final solution plus the initial solution minus the final solution, exponential minus t over C. So whichever you're comfortable with, it's okay. Okay. And then you may want to run the validation to be sure that if this is truly the final solution, and this is the initial solution, which is explainable, okay? And for us to verify, so when t equal to 0, for instance, we already know V of t to be equal to VA plus V naught minus VA exponential minus t over RC, right? So when t is equal to 0, so V of naught, so let's see if we're going to get initial value, right? It will be equal to VA plus V naught plus VA exponential minus 0 over RC. So this will reduce to VA plus, this is minus V naught minus VA exponential 0, right? So that's VA plus V naught minus VA times 1, right? So that will be VA plus V naught minus VA. VA minus VA, so V of naught is equal to V naught, which is the initial value, okay? What if t tends to infinity? That is at t greater or equal to 0. So this will be after 5 time constants. Okay, so it means we have V infinity, which is equal to VA plus V naught minus VA exponential minus infinity over RC, right? So anything over infinity, negative infinity is 0, right? So this is going to give us VA plus V naught minus VA times 0. So V infinity is going to give us the final value, VA, which follows directly from what we have discussed. So hence, we've been able to evaluate the total or general solution to a series RC circuit. So in the next lecture, we'll consider parallel RC circuit.